Okay, to date, we have covered pipe schedule system and also estimating a water supply. Now we're going to deviate and look at a different way of developing a sprinkler design. The pipe schedule is based on the concept of providing a prescribed um, configuration of piping at a certain pressure at the base of the riser, along with a flow and a duration of flow. Um, but it never really specified the flow at the end point at the actual sprinkler. And now with this density area concept, we are going to now specify what that number should be, what that actual flow should be through the sprinkler head, as part of what we refer to as a hydraulically calculated system. This is for entertainment purposes only. It's my opinion. As we go through this, you'll see that it's rather nuanced. It can't be simplified. Some things do fall right into place and others don't. Makes it difficult sometimes to come to a final analysis on what exactly where an occupancy should sit. I've held off to this point describing occupancy types, but I knew that we would need to get to it. And so NFPA has defined various types of occupancies, and it's really based on the combustibility of contents. Light hazard occupancy, I'm paraphrasing the actual definitions, that quantity and combustibility of contents is low with a low heat rate of heat release. So what we're looking at is occupancies that won't burn rapidly, don't have a lot to burn. Offices, churches, hospitals, museums, and educational institutions. Now, if you were to say to me, boy, those don't seem like light hazard occupants to me. They do have quite a bit of contents that would burn. A lot of insurance companies would agree with you, and they don't even acknowledge that there's a light hazard occupancy out there. However, NFPA does. NFPA is the standard that is referenced by most codes. So for our purposes, there is a light hazard occupancy, and it does consist of those types of occupancies. Moving up to more hazardous operations, we have an ordinary hazard group 1 occupancy, and definition is combustibility is low, quantity of combustibles is moderate, stockpiles do not exceed 8 feet with a moderate heat release rate. And that would be bakeries, dairy plants, laundries, electronic plants, beverage manufacturers. If you've ever walked through any of them, they don't have a high combustible loading. So that would be group 1 occupancy. There's a ordinary hazard group 2 occupancy, and that is still within the same realm as group 1, but a little bit more moderate combustible contents. Machine shops, they will have some oil, fabrication of plastic, a really difficult subject, but I included it in there because there are some plastic operations that truly are low to moderate combustibles, ignoring the storage that they have on site, which is a different issue. Mercantile type operations, barns and stables, and post offices. They again, there's a combustible content to this space, but it's more than the group 1, and it's less than what we'll next see. And that next group is a step up to extra hazard occupancy group 1. Quantity of contents is very high, or dust, lint, or other materials present introduce the probability of a rapid fire with high release rate. So die casting, metal extruders, textile operations that have lint and dust, rubber manufacturing, plywood. I mean, all those operations that have some element of combustibles make for a more hazardous operation, which is why it's grouped above the ordinary hazard occupancy. And finally, as part of the occupancies groups, we have the extra hazard Group 2, occupancies with moderate to substantial flammables and combustible liquids. That would include plastic liquid spraying, include plastic manufacturing. Now, if you recall, I had plastic fabrication in the ordinary hazard. And there's a clear delineation between the two, with one having substantial quantities of hydraulic fluid under pressure, which represent a significant fire loading, solvent cleaning, oil quenching, operations that have a significant amount of flammables in their operation or exposed combustible liquids. As you noticed, I have not discussed storage in any great detail. For those people who are just on the cusp of sprinkler knowledge, the architects, real estate people, that sort of thing. Once you're outside 5 feet of plastic storage, or I'm using 8 feet, although 12 feet is kind of the standard number, you really need to be speaking to a professional, a sprinkler professional, to get further information as to whether or not the sprinkler system will be adequate. We haven't discussed storage to any great length, and that's because it's its own topic, and there's a significant amount of knowledge you need to make informed decisions. So right now we're just dealing with occupancies and low quantities of storage. My apologies for the distortion to the graph there. That those should all be straight and not kind of distorted like they are. In any case, this is the area density curves, kind of the basis for design for hydraulic systems when we're looking at occupancies. As we discussed, is the light, two ordinaries, and two extra hazard designs. Been around since the early 70s, I think since 1972. And as you can see, let's just take one of those. Let's just take the ordinary hazard group 1, for instance. What it says is that there's a area of sprinkler operation along the y-axis, and that runs from 1,500 to 5,000. Then there's a density, which I'll get into in the next slide, which is an area of water, which is a quantity of water being applied to a square foot space. And for the ordinary hazard group 1, it has this line that extends from the bottom of 0.15. And if you draw across to the y, it's 1,500. And up at the top, it would be 0.1 at 4,000. And what that curve does is it allows for you to, as the designer, to choose anywhere along that curve for your design criteria. So for instance, you could choose 3,000 square feet, 2,500, et cetera, et cetera. And that's the true with ordinary hazard 2. And then you can see it, the extra hazard group 2 starts at 2,500 and runs up to 5,000. The same concept. We have like 0.28 over 3,000 for the extra hazard group 1, or 0.3 over 2,500. So this has been in place for many years. There's a dramatic change in the 2022 NFPA 13, where they've gotten away from this being able to slide up and down the curve, and essentially now you have points. So for instance, the ordinary hazard group 1 now would have a point at 0.15 over 1,500 or 0.12 over 3,000. So you can't slide up and down the curve anymore. These area density curves will still be in place for existing systems, but going forward, the point curves, not curves, but the points that the over 1,500 to 3,000 square feet will be all used for all new systems. Let's get into this design area first. So what we have before us is a tree system. those little circles are representative of a sprinkler head, and the piping is a tree system with the center fed tree system, and there's 12 feet between spacing, 10 feet between branches. There's a dotted blue line, and what that dotted blue line is the design area. And so what it says, NFPA says to the designer is what you need to do to meet the sprinkler requirement is to provide a certain amount of water within a design area. Now, the design area is beyond really the scope of this topic. It has to be based on a certain configuration, and other insurance companies have different requirements from NFPA, and I don't think it's really germane to what we're discussing here. But know that we're not we're not calculating the entire system flow. We're calculating the flow over a very, very remote area, a very small area. Let's just say the sprinkler system covers 50,000 square feet. Well, we're only looking at that flow area, maybe over, depending on what that graph is, from 1,500 to 3,000 or 4,000 square feet. So that dotted line represents the sprinklers that'll be flowing for our calculation purposes. Now, what does the density mean? Let's not complicate this. This is a very simple idea. All it's saying is that within that dotted line, every square foot must have a certain amount of water hitting the ground. And if you recall that the graph on the prior slide, for instance, for light hazard, it had a number of 0.1 gallon per minute per square foot. And what it was saying is that for each square foot within that 1,500 square foot design area, you are required to supply 0.1 gallons per minute. If we step up to some of the bigger numbers, it's still the same concept. If it was an extra hazard, at group 1, where we required 0.28 over 3,000, it's telling us that for that 3,000 square foot design area, you are required to, within each square foot of that design area, you must provide 0.28 gallons per minute. It's no more complicated than that. It's actually a very, very simple concept. I'm getting slightly ahead of where I want to be because I'm also going to be backtracking in the next video a bit, but I do want to cover this concept. If we know the design area and we know the flow within that design area, we can calculate a minimum flow over that entire design area. And all that is you multiply the design area by the density. So for instance, if we had a system that was 0.17 GPM per square foot over 3,000 square feet, multiply 0.17 times 3,000 to end up with 510. 0.15 over 1,500, 225. And I'll leave that to you to do the 0.28 over 3,000. So we know at a minimum when we have a 0.17 GPM per square foot system density over 3,000 square feet, we must have a flow of 510 GPM. Again, getting slightly ahead of ourselves on the discussion, but I do want to throw this out as a teaser. So let's just say, for the sake of discussion, we're flowing through 4 heads in a 125 system. If you recall what the 125 system is, it's one head being provided by 1 inch, 2 by 1.25 inches, and 5 by 1.5 inches. And so in this particular case, I've got 13-foot spacing between heads, 10 foot between branches. I included 2 T's because it's going back to a cross main. And so the overall sprinkler head covers 130 square feet. Based on the prior slide, each head covers 130 square feet, and we have 4 heads So that would mean that each head is providing 19.5 GPM times 4 is 78 GPM. But when we actually do the flows, it's 85.4 GPM. Why is the actual flow higher than the minimum flow required? I'll leave that right now as an open-ended question, and we'll come back to that, not in the next video, but the video after that. So sometimes classifying these occupancies are simple, and sometimes they're not, and sometimes they're different occupancies depending on where you are within the space. So for instance, a woodworking shop's pretty straightforward. You're likely, Xing out any kind of storage per se. You're looking at as an extra hazard group 1 occupancy, fair amount of wood on site, scrapings, that sort of thing. Shopping malls, interesting, mercantile operation. However, here's a great example of areas that have significant storage. So you might have a front end mercantile operation, but in the back you've got 3, 4, 5,000 square feet of rack storage to 20 feet. Well, these smaller densities are certainly not going to provide protection for these for these inventory areas. So we really need to be able to split out those operations. Metalworking operation mostly will be considered a ordinary hazard group 2 operation. Plastic injection molding, that's a great topic. If you're in the business, in the insurance business or an AHJ, there's a whole realm of conversation to be had on this topic. Most people will come down with at least an extra hazard group 1. Some may classify it as an extra hazard group 2. In smaller quantities, it may actually be something smaller than that. It's I put that in there because it's not a cut and dry answer. It really depends on you looking at not only what the operation says it is, but the quantities that are involved. The textile operation with the lint and dust and that sort of thing would be an extra hazard group 1. So what we've done is we've been able to define the different types of occupancies, and we've been able to work off this graph that will now give us an area and density of for a design area, and we're going to move on from that for the next video. In the next video, 7B, I will do a short video on what I'll do is outline how to distinguish between a pipe schedule system and a hydraulically calculated system. It's a lot easier than you think. So see you in the next video. Bye now.